So we'll be solving this problem on finding the properties of transfer function and using the final value theorem to find out the value of the output when t goes to infinity. So this is a problem from this textbook by Seborg, 3rd edition. So we are given a transfer function for this case, which is given as 5 over 10s plus 1. So it's the first order transfer function without any delay term. So we have been asked to find out what is the steady state gain of the process, and then find out what is the time constant of the process. Then in part C, it gives an input signal and you are asked to find out the value of the output when t goes to infinity. Part D, so it asks you to find out first the value of the output at t equals 10, which is the time constant of the process, and then find out the value of the ratio of the output at t equals 10 to the value of the output at t equals infinity. Okay. Part E, it gives another input signal, which is a pulse type of input, asks you to find out the value of the output when t goes to infinity. Part F, it's a similar problem, however for a different type of input, which is a pulse type of input given ut equals delta t. And then the final part, again it asks you to find out the value of the output at t equals infinity for a sinusoidal input signal. So we are given a transfer function, which is given by 5 over 10s plus 1. So it's a first order transfer function without any delay term. So the first part, it asks you to find out what is the value of this gain of the process. The second B, it asks you to find out the time constant of the process. Now part C, it gives the Laplace transformation of the input signal. So us over 2 over s, meaning that's the step input with size 2. So you are asked to find out what will be the value of the output when time goes to infinity. And then the part D, it asks you to find out the ratio of the value of the output at t equals tau to the value of the output when t goes to infinity for the same input signal, that's the step input with magnitude 2. So you need to find out the ratio. Part E, again it gives another input signal, and if you look at this input signal itself, it's a pulse input, it's a rectangular pulse, and again it asks you to find out the value of the output when t goes to infinity. Part F, again it asks you to find out the value of the output when t goes to infinity for an impulse signal. The time domain expression of the input is given for this case. Then finally for part G, you are given a sinusoidal input, and for this case you are asked to find out the value of this output when t goes to infinity. Now let's analyze the problem and look at what approach will be following. So one of the main steps in solving a problem is to analyze the problem first and to figure out what you have been asked to do. Do remember that in the exam you'll see a total new problem that may have some similarity with the problems that we'll be solving during the class hours or as part of the assignments. However, the exam problems will be new, so you need to apply those concepts to solve a new problem. And for doing that, one important step is to look at what you have been asked to do. And that's because sometimes you may not be asked to solve a similar problem, rather a part of the problem. In that case, if you do not really focus on exactly what you have been asked to do, you may be wasting time, and which is very important during the exam. So let's look at the problems. So look at this part A and part B together. These two are nothing but to find out the properties of the process. And you know that for this case, so for part A and B, you'll have to express the input. So you have to express the transfer function in its standard form. So for a first order transfer function, the standard form is given as k over tau s plus 1 when there is no delay term. And then the term k will denote the gain and the term tau will denote the time constant. To remember that in the standard form, this should be 1. So if this value is given as something other than 1, so you need to divide the entire transfer function by that particular value to get that term to be 1. Now part C, E and F, all these ask you to find out the value when t goes to infinity. So for this case, you can take different approaches. For example, you can find out the expression for yt and plug in the value of t equals infinity. Another approach would be to use the so-called what is called this final value theorem. So what this final value theorem tells you that the value of a function when time goes to infinity can be found using the function in the S domain or the Laplace domain by putting s equals 0 and multiplying the function by s. Okay, again, the final value theorem tells you the value of a function at t equals infinity equals the value of the function times s when s goes to 0. So if you, for this case, if you find the expression for yt, you can plug in the value for t equals infinity, or if you know what is ys, you can multiply it by s and then plug in the value of s equals 0 to get the value of the function in the time domain when t goes to infinity. So for our case, we'll use this final value theorem for this part C, E and F. Now for part D, it's a special problem where it says that you have to find out the value of find out the value of the output when t equals tau to that of the output when t equals infinity. Okay, so for this case, you need to go back to the basic definition of this, what is called this 63.2%. What it really says that the value of the output when t equals the time constant is 63.2% of the value of the output when t goes to infinity. So you can use that directly to find out this ratio. Now the last part is part G, which will require a little bit of extra treatment here, simply because the final value theorem is not applicable for this case, and we'll discuss that in details. Okay, so now let's give a pause for a few minutes and using those analyses try to solve the problem and then come back. Now let's look at the solution. So for the first part, we need to write down the transfer function in its standard form. So for our case, the transfer function really is given in the standard form, which is 5 over 10s plus 1. So this term is already 1, so we don't need to standardize any further. And then we can find out what is the value of k. So k equals this number here, which is the gain. And what is the value of this time constant? This time constant is here, so tau equals 10. So that's straightforward. Okay. Now part C, we'll use this in the final value theorem. For this case, we need to express ys equals gs us. So for our case, for this one, us equals 2 over s. So ys becomes 5 over 10s plus 1 times 2 over s. So we got the expression for ys. Now we need to use the final value theorem to find out the value at yt equals infinity. So we know that limit t goes to infinity yt equals limit s goes to 0 s ys. So we have s times 5 over 10s plus 1 2 over s. So this s and s gets cancelled out. To plug in the value of s equals 0, we have this to be 10. So that's for this particular step input with size 2, the value of the output at t when t goes to infinity is 10. Now for part D, we said that it's 0.632 or 63.2%. So you can directly use our knowledge on that part. Now for part E again, we'll use the same final value theorem. For our case, we have limit s goes to 0. We have 5 over 10s plus 1. And we have the input to be s times 5 over 10s plus 1. 1 minus e to the negative s over s. And if you plug in s equals 0, so this s and s gets cancels out. S equals 0, this will be 0 plus 1. So this 5, and this part will be 1 minus e to the power 0, which is 0. So we'll have the value to be 0. So for part E, when t goes to infinity, the value of the output is 0. For again part F, we have ut equals delta t, which is an impulse input. So we'll have us will be 1. You know that the Laplace transform of the impulse is 1, and we directly use this final value theorem here. S so plug in this value over here, so it becomes 0. So for this last part, know that ut equals 2 sine 3t. So we have us equals 2 3 over s square plus 9. That will have, you know that the Laplace transformation of sine omega t equals omega over s square plus omega square. So for this case, we see that ys is 5 over 10s plus 1, 3 over s square plus 9. Now for this case, we cannot apply the final value theorem, because final value theorem is applicable for a function which has its poles strictly on the left hand side plane. Okay, so for this case, we have this pole on the imaginary axis. So for this case, the final value theorem is not applicable. So in other words, if a function really does not converge to a final value, the final value theorem is not applicable. Okay, so now we'll see that if you try to find out the value of yt, you need to take the inverse Laplace, and you see that this yt becomes also a sinusoidal, meaning that yt will behave something like this. So yt equals infinity, it does not converge to one final value. Problem D, which also asked you to find out the value of y when t equals tau. Okay. So for this case, we know that for this case us was given as 2 over s. So ys will get as 5 over 10s plus 1, 2 over s. Now we'll use the inverse Laplace formula for this case to get the expression for y equals for yt. So we know that if we take Laplace inverse of this km over tau s plus 1, it becomes km 1 minus e to the power negative t over tau. So for our case, we will have yt equals the value of k being 5, value of m being 2, 1 minus e to the power negative t over tau equals 10. Okay. So for this case, if we plug in the value of t equals 10, we'll have 1 minus e to the power negative e to the power negative 1, and then this entire term becomes 0.632. So we'll have this to be 10 times 1 minus e to the power negative 1. We plug in t equals 10, and we'll have 10 times 0.632. It becomes 6.32. So that's the value of output when t goes to